All right, we're going to talk a little bit about mother functions today. I'm going to try to do this in one take, be the one take wonder. Parent functions or mother functions are basically the most simple form of an equation, and there are sort of different equation families. Let me go to our whiteboard here. So all of you guys who are doing my mother function project, hopefully this video will help you. All right, so when we're talking about mother function project, when we say mother function or parent function, change this color here. That is not a good color. There we go. Parent function, what do we really mean? We mean the most basic form of any kind of function. So let's start with lines, because we all start with lines in algebra. And if we have a line, the most basic line we can have is y equals x. Okay, and all lines thereafter kind of become variations on y equals x. You might take that and give it a coefficient of 2. You might take it and say, I'm going to add 3 to the end. Now we have both of those things at once. And this should start to look familiar, because once you get here, we know this as slope-intercept form. So we're really going to look at how adding these things, this coefficient and this y-intercept, changes your original function. Lines become pretty straightforward about this kind of thing. Then sometimes we're going to get into parabolas. I mean, sometimes you just have to square your x's, right? This is the mother function for a quadratic equation. And obviously, just like you can with lines, you can do things to this. So we're going to look today at how each of these different things that we do to different functions changes them in their graphs. We're going to look at their graphs, and we're going to watch how their graphs shift around, and we're going to try to find some patterns across all of these functions that should apply to all of these graphs going forward in algebra. So let's do this. All right, let's look at Desmos. Okay, so start with our basic function here. We've got y equals x. That red line right there, that is your parent function. Okay, so now we're going to look at what happens when we have y equals 2x. That blue line shifted. It tilted so that it's a little bit more steep and it's closer to the y-axis. Okay, interesting. So what do you think is going to happen if instead of 2x, we do 1/2 x? Let you think about that for a second. It gets flatter, closer to the x-axis. This kind of makes sense if you understand the concept of slope, because any coefficient of x there on a line is the slope. And so the slope being steeper brings the slope closer and closer and closer to vertical. Vertical, of course, being totally undefined. And the slope being smaller, 2 is going to be steeper than 1/2, because 1/2 is closer to 0. And a slope of 0 is going to be just straight on the line. There we go, that blue line. Doesn't like that very much. Okay, so we know that whole number slopes seem to make the line get steeper. Fractional slopes make it get flatter. What happens if I make it negative? Yeah, flips around. Okay, and you'll see that it sort of just becomes the opposite. It flips it over. So negatives, in terms of coefficients, negative coefficients will sort of flip. Negative leading coefficients will flip your graph around. Okay, and that's true even if it's negative 2x or negative 0.5x. Okay, so now let's look at what happens starting with our mother function if we just add something. A lot of times I have students say, oh, it shifted over. Well, I mean, I suppose the x-intercept did shift over, but really what we're looking at here is our y-intercept. Every value that originally just would have been itself now has 3 more, so if it were 0, now it has 3 more, so there it is at 3, 0, 3. Okay, so that's the concept of the y-intercept. Most people are pretty comfortable with it. So when you add something, it shifts it up, and then I'm sure it will not be surprising, therefore, to know that when you subtract something, it shifts it down. Line's pretty straightforward that way. Okay, let's move on to something a little more fun. Let's go into x squared. Let's look at some parabolas. All right, there's the parent function or the mother function for the parabola. Very basic. Y equals x squared, the origin of all parabolas. And now we're going to go over here. This is not yet being shown, but y equals x squared, but let's give it a coefficient, shall we? Let's give it a coefficient of 4. And let's show it. So when we had lines, we noticed that it got steeper, sort of closer to vertical when we had a whole number coefficient, whether that was, as long as it wasn't a fractional coefficient, as long as it wasn't between 0 and 1 or -1 and 0, as long as it wasn't in that range, it made it steeper. So let's look at what we've got here. Interesting. Let's add another one. So steeper there, y equals x squared. And let's make that 1/4. And that third one right there, 1/4, made it wider. So again, I'm just going to hide this one real quick so you can compare. Red line, parent function. Green line, related function. Okay. Number greater than 1 or less than -1, like a whole number, is going to make it skinnier. Okay. And if it's between 1 and -1 on the number line, it's going to be wider. Okay. All right, so now let's look at what happens if we just make that negative. Any guesses? Give you a second to think about it. When we had a negative slope, it flipped it in the opposite direction. Parabolas do not have slope. I'm going to say that again because I always have to repeat it to my students. Parabolas don't really have slope. We don't really use that word for parabolas. They can have the slope of a line at a defined point, but that's a little thing for calculus later. Right now, we're just looking at what happens when we make our leading coefficient negative, and it flips over. It's not the slope changing. It's not a slope, but the parabola itself, all the values become negative, so it flips itself. So far, in lines, a negative sign flips something, and in parabolas, a negative sign as a leading coefficient flips something. Seems we're onto something there. So in a line, when we added 3 to the end of it, it shifted the line up 3. Oops, I hit equal sign. Plus 3. And you see it's the same thing. A lot of times people ask, oh, are they ever going to cross? Are these parallel now? No, they're not parallel now. Parallel is not really what we would call these. They are just a parent function and a parabola that has shifted up. Now, let's see. Same thing, of course, if we do our -3. There you go. Shifts it down. So with this in mind, we're not going to look at the middle coefficient. I know there's much more complex quadratics with a middle term. We're not going to look at those right now. Just going to keep it to the basics right now. But let's make a prediction. Let's say I make this 1/5 x, y is equal to 0.2, 1/5, 1/5 x squared minus 4. Now, you know what, I'm going to do -2. what's going to happen? We want to make a prediction. So we see, okay, that is a number that is between 1 and -1 on the number line, right? It's a fraction less than 1, and so we know that it's going to get wider and flatter because it's going to be closer to 0. So we know that the parabola is going to open up, and we know -2 that it's going to shift down 2. So then even more, what happens if we make it negative? Well, now it's flipped over, open wider, and shifted down 2. Let's take a look. See? There you go. Shifted down 2, open wider, and flipped upside down because negative makes it flip. Fractional leading coefficient between 0, or between -1 and 1 makes it open wider. -2 shifts it down 2. Okay. Let's get out of parabolas for a bit. Let's do square root functions. Here, y equals the square root of x. There we have it, our beautiful square root function. The parent function, the origin of which sort of looks like a parabola that got chopped in half and tipped on its side. And the reason it isn't just a parabola tipped on its side, of course, is because it wouldn't be a function if it had a bottom part, because it would have 2 domains, or 2 ranges for 1 domain, which is a no-no. So let's look at what happens when we have y equals the square root of x. And now let's give it a coefficient. So previously, in lines, what happened when you had a coefficient of 1? Or not of 1, I'm sorry, a coefficient of like 3. Got skinnier. Coefficient of 1/3 got wider. Tilted, closer and flatter, closer and flatter. Parabolas, wider and narrower. So let's say we give this a coefficient of 5. What's going to happen to this? Is it going to get steeper or is it going to get flatter? Well, 5 is not between -1 and 1 on the number line, so it's going to get much steeper. That looks crazy. Let's make that 3. There you go. Still looks like a square root function now. Okay. Now what happens if, again, this were 1/5? Oof, very flat. Okay, so in general, once again, fractions that are between -1 and 1 flatten out a graph. Anything else on either direction? Okay, going from -2 on down to -infinity, and not even -2. I mean, technically -1.3. I mean, anything smaller than -1, anything bigger than 1 is going to make it steeper. Okay. All right. So let's look at this and make it negative. Any guesses? Probably. I'm sure you won't be surprised to see that it flips upside down when it's negative. Now it looks like a whole parabola. Flips upside down when it's negative. Remember that that pink part is no longer. That's 2 separate functions there. Right? 2 separate functions. There's one. There's the other one. Okay. So negatives, again, shockingly, flip it upside down. No big surprise. And if we are outside, here's where square roots are fun. If we are outside of that, and we add 2, it shifts up 2, just like it did when it was a line, just like it did when there was a parabola. It'll shift it vertically 2, or of course, if it's subtracted, oops, 22, oops, -2, there we go. It shifts it down 2. Okay. Now, what happens when we're underneath the radical? This is where it gets a little bit weirder. I'm going to go ahead and do -2. So it didn't shift up or down. It did, however, shift to the right. And if I do +2, it shifts to the left. So wait a minute, why is it that if this is +2, this shifted the graph in the negative direction? That's super not intuitive. Why? Because when you do plus 2 on the outside, it shifts it positive 2. When you do minus 2 on the outside, it shifts it negative 2. Why is it reversed as soon as this thing gets under the radical? To get the answer to that, you kind of have to think about what you would plug in. So if I plug in the value of negative 2 into this equation, I now have negative 2 plus 2. Negative 2 plus 2 is 0, and the square root of 0 is 0. So we have the value negative 2, 0. Input negative 2, output 0. If we plug in 0, right, we plug in 0, we get 0 plus 2. 0 plus 2 is 2. The square root of 2 is about 1.4. There you go, 1.4. We cannot have anything past this. We can't plug in negative 4, because if we plugged in negative 4, we'd have negative 4 and positive 2 is negative 2, and then we'd have a square root of a negative, and then imaginary numbers doesn't happen. So the graph doesn't go out that far. So in order to get this, input minus 2, right, there you go. If I tried to plug in 0 here, the same thing would happen, right? If I tried to plug in 0, I'd have the square root of negative 2. You can't have that, so it can't intercept the origin right there. It can't have a value for 0. This graph, that's an excluded value for this graph. It doesn't happen, okay? So that's why that happens. So again, in quick review, 4 square root functions. You have the basic in red. In blue, underneath the radical, if you have something that is minus 2, it's going to shift it to positive 2 to the right. Negative 2 happens when you add 2 underneath the radical. Then, if you just multiply it by a number that is kind of a, quote, whole number, it gets steeper, all right? If you make it negative, it flips upside down. If you make it a decimal, or between negative 1 and 1, it flattens out. And if on outside the thing we have minus 1, look at that, it shifts it down 1. And then we're going to shift it back over just for fun. Plus 4, look at that. That's wild. This looks like a very complicated equation over here. If you saw this and you're like, graph that, you might go, blah, no, what? And if you saw this and just looked at it, it might be hard to think for a second, wait a minute, how could I actually generate the equation of this? But looking at these together and seeing how they shift, you can see how they're related. So here you can see it is down 1, so you know there's going to be a minus 1 out there. It is almost at negative 4, which means you know there's going to be a plus 4 underneath the radical sign. And it's a little bit harder. You know there is going to be some kind of a negative sign because it's inverted. Exactly how flat it is would be hard to determine without a little crunching the numbers. But everything else about this you could determine, right? If this didn't have a negative 0.2 on it, and you see that it's the same curve, you could probably figure that out. Okay. Let's look at exponential functions. Y equals, where's my, where's my keyboard? Y equals, no, we're not going to have an x to the anything. There isn't really a parent function for this because the base changes every time. So we're going to just use 2 as our kind of parent function for it. We're going to use base 2 and 2 to the x. Okay, beautiful exponential curve. So you'll notice things about exponentials. First thing I want you to notice is what happens when we take y equals 2 to the x, and instead of 2, we change the base. Let's make it 3 to the x. And let's make this one 4 to the x. Okay, here's 3 to the x. And here's 4 to the x. they're getting steeper. But they have one thing in common. They're going through 1 as their y-intercept. This is because this is to the power of x. That means here we plug in 0 as our value of x. And when you plug in 0, anything to the power of 0 is 1. So anything, without any messing around, that y-intercept is going to stay right there. Okay, if you don't have anything else added to it and you just change the base, that y-intercept is going to be right there. Now, let's look at what happens if we do 2 to the x, but we add 2. Anyone want to guess? Plus 2. It shifts up 2. So that y-intercept changes now because it normally would have been 1, but we've added 2 to it, so it goes up to 3. Okay. This here could be considered the y-intercept of a line, but it cannot be considered the y-intercept of an exponential function because there's other stuff going on. Okay, plus 2 shifts it up, and we can talk a little bit here about how this line approaches 0. 0 is a horizontal asymptote of this graph. So this is also, because it's shifted the whole graph up 2, it's got a horizontal asymptote of 2. So while we can't say that that's the y-intercept, we can say, oh, that right there, that's the horizontal asymptote. Whenever you need to find that, you can look at the end of the function. Okay. Now, let's see what happens if we make this negative. And I think that nobody's going to be terribly surprised here. Yeah, flips it upside down. Okay. Negative flips it upside down, and we'll just keep that in the pure form here. There you go. Looks like they go from the same asymptote, except this one, as the numbers increase, it increases, and this one, as the numbers increase, it decreases. Okay, so that's what the negatives do. And something else to think about, what happens if instead of 2, we pick that value that is between 1 and negative 1? Let's make it a fraction. Let's make it 1/5 because it's easy. 0.5. Whoa, what? That completely... Okay, some people are going, wait a minute, it flipped in a completely different direction. Why did that happen? It didn't flatten or anything. It just like went in another direction. Well, in fact, actually, since it's 0.2, I'm going to make it 0.5 so you can see it's a perfect mirror. There we go. So now we have a base 2 and a base 1/2. They're reciprocals, so you can see it's symmetrical. What's happening here is you have to think about what happens when you have a power of a fraction. Right? You have a fractional base. 1/2 times 1/2 is a 4th. Times a half is an 1/8. So it's going to get smaller as it goes down. So this is what we call exponential decay, and this is what we call exponential growth. Okay, so something a little bit different to think about here for our exponential functions. Okay, let's talk about, let's go back to our base here, and let's talk about what happens if I multiply this by something, because the standard form, as much as you can have a standard form of an exponential equation, is a b to the x. So something times a base to the power of x. So let's have a base on this one. Let's have times, oops, I should have that in the wrong place. Oh, wait a minute. 2 times 2 to the x. This one is the same thing as 1 times 2 to the x. That's the same now. Okay, because that was just 2 to the x. Multiply times 1 is the same, right? The mother function stays the same. 2 times 2 to the x. Let's mess with this one. Let's go 3 times, oops, I had to put s, 2 to the x. Let's see what that looks like. Oh, so now not only are we getting steeper, but we're actually changing the y-intercept. So at 1 times 2 to the x, which we don't even bother to write, we just call it 2 to the x, it's going through 1. At 2 times 2 to the x, it's going through 2. At 3 times 2 to the x, it's going through 3. Anybody want to guess what's going to happen when we have 4 times 2 to the x? Yeah, it goes through 4. So, hey, this actually does affect our y-intercept. With nothing else, with no other shifts to mess with the horizontal asymptotes, and no negatives, this number right in front, this a value that gets multiplied to the base, can actually act as our y-intercept. All right, and that makes sense when you think about like, oh, it's the starting point of an investment. You know, you have to start off with, at 0 amount of time, you invest $4. That's your starting point, right? So that's the shifts for that. So now we should be able to look at some of these functions, and we should be able to just sort of guess what's going to happen. So let's try. Okay, let's try a new one. Let's say we have a function that is y is equal to negative 1/4 I did not mean to do that. -1, there we go, 0.25 to the x. Wow. So look at what happens here, right? There's the parent function. The negative sign flips it over, and the fraction flips it in the other direction again. If this were just 2, you see how we just go there, but since it's 0.2, it goes in the other direction. And then 0.25 makes it a 4th, so it just shifts it a little bit. Okay. All right, so to sum up, look at your graphs, look at your equations, and there's so much you can know, and if you need to match them up, there are lots of little clues. Negatives go flip, and you have to think about leading coefficients. Are they numbers that are between 1 and -1, or are they bigger than 1 and smaller than -1? Because that's going to affect how it opens up or tilts. And does it have a plus or minus at the end, and is it underneath something? In case of these, is it, when I say underneath something, I mean, is it underneath the radical or outside the radical? And then you also have to pay attention to the base and the a term that comes in front of the base, that gets multiplied to the base. Okay, so many little things to think about. All right, I'm signing off. I'm going to open it up for any questions if anyone has questions. I am happy to help. You guys know how to reach me.